Okay, now that so far what we have seen was that we were able to use, I should say, the dense overlay plots in the Bayesian, I should say, in the Bayesian frameworks to do a kind of a posterior predictive check in order to see the replicated data. They are in the close exactness, I should say, with the true values that we have just built the original model with. Another thing which you want to do as a culmination to these, I should say, to these checks, to just go ahead to introduce another function, which we go ahead as it's going to be PP, I should say, PP check, which stands for posterior predictive check. The format which this function has, which is R stand arm, it's a very straightforward method, and you can see that the thing that we can just use and put inside the functions is somehow much similar to the things that we have done. In order to see what arguments that we need, on the previous examples that we had to just, when we just use the Boxplot, for example, in the histogram that you saw, we had to just use the true values of our data and also the replicated values of the data, essentially a matrix which shows that the rows that we had from the posterior distribution. However, with the PP check, we do not need to just do the draws first. We can just go ahead with the model first. For example, I just go with the model A, which it represented, I should say, the model which we had for a Bayesian regression analysis, in a way that in our Bayesian regression, we had a linear relationship between the response variable and the predictors and covariates. A linear relationship, I mean, between the woman's height and the woman's weight. And we just stored that Bayesian analysis object into a model which is model A. And if we just go ahead with that one with only one option, you will see that the thing which you get, it's somehow so similar with the plot that we had when we just use, I should say, PPC dense overlay. Then we had our true values, replicated values, and that's how we did. However, what we want to do here, we're just going to just add some arguments to get the box plot. On the next argument, I'm just going to go ahead with the plot the function of the plot. I'm just going to go ahead inside, I should say, inside the quotation mark, add Boxplot. And also, I'm just going to go ahead with the number of the replications, which you said that it shows that there is a menu which opens here, and it says that the nreps represents the number of the replicated data that you generated from the posterior predictive distribution. Okay, and you want that it to be shown on your, I should say, on your data sets. For example, if I just go ahead and say, okay, I'm just going to go ahead with the first 10 rows which I got from, I should say, from the posterior distribution, I'm going to go ahead and execute that line, and you will see that the outcome is going to be this figure. You will see that we have some box plots. With the box plots that we have created, we have the dark blue represents the box plot of our true values. Before we just go ahead, I'm just going to add one more argument to the functions that we have. It's going to be, I should say, the notch, and you will see the difference which it causes. It cuts the upper part and the lower parts, I should say, of my data. And if I execute it, you see a better presentation of the box plots. In the linear model, you will see that the box plots that we had, the box plot, which the color of it is a dark blue, it shows that, for example, the median, that it relates to some basic statistics of the true values of our response variable, which here is the woman's height. We see that the median, the average human height, somewhere around 65 inches. We had the first quantile and also the third quantile of the woman's height. Means the first 25% of the heights, the 50% of the heights, the average of it, and also the 75% of the heights. The first, the median, and the third quantiles of the true heights of those women. But you see that if I come here, for example, if I just put the number of the replications is going to be 1, you see that on the first samples that we get from our posterior distribution, we have a vector of the prediction of the woman's height, which the first quantile and the median and the third quantile of all those 15 women has this kind of relationship with the true values of the woman's height. That imagine that we just said, for example, we can have as many samples that we want. We can take as many samples and throws from the posterior. Let's go ahead to show the 15 samples from this. Then you will see that the values that we have, it's going to be somehow like this. You will see that the true values of the height, if, as I said that to you, the first quantile, the median, and the third quantile is this, on the first row, which the first samples, we generate a vector of 15 American women's height, which their statistics is represented by this box plot. On the second attempt of the sampling, we get this one, the third, the fourth, the fifth, and it goes on until the 15th. You will see that if you were able to produce a much closer replication to the original data sets that you started with to just build your model, then you expect that you should exactly have the same box plot at least. But you see there are some variations. If you just trace the means, you see the means, they just follow some variations. It goes down, up, and goes up, down, up, down. However, it was the box plot of the model that we created in that manner. It was the box plot, let me just add it as a line, it was a box plot of the linear model. Now, we want to do the same thing with, I should say, with the box plot of the quadratic model. What do I mean? I come here again, I said, okay, the PP check, which is essentially the posterior, I should say, predictive posterior predictive check. It comes with the R stand R, then you do not need to just install the base plot. It's essentially just within the same package that you have built your model with. I said this is a check. I'm just going to go ahead. We know that the quadratic model was called model Q. It was a quadratic model that we had the quadratic terms with respect to the woman's weight into the model which predicted the woman's height from it. Then now I'm just going to go ahead. I'm just going to go with the plot one. In the graphics, I'm just going to put the box plot. And also, with the number of the replications that I just want to show, let's go ahead again with the 15. Let's go with the 20 this time to make some changes with respect to the linear models which we had. But that depends on your choice. You can just plot the number of the replications from 1 to 20 to 100. It depends on how you just want to what extent you want to see the variations between the replicated data and also the true values of the data. And also I'm just going to put the not equal to false, which in that sense I should say, a clear representation of my box plots. The code is ready. It needs just to be implemented. I'm just going to press Control Enter to execute the line, and you will see that the plot is being produced. Now, this model seems much better than the linear ones which we had. You see that there are less variations, at least if you just want to trace the mean of our data sets. The mean of our data sets and the size of the box plots, you see that they do not make big differences, which shows that the quadratic model in our Bayesian regression analysis is more acceptable, at least if we compare that into the linear model that we just came up with that initially. And now this is going to be for the quadratic model. And now, as the very last one, it's good also to just do a box plot of the cubic model that we had. I'm going to go ahead with the posterior predictive, I should say, check. I'm going to go ahead with the model cubic, which it has the quadratic plus the cubic term of the weight in the model which predicts the woman's height from its weight. I'm going to go ahead with the plot one, we are just going to produce, I should say, the box plot. I'm just going to type it inside, I should say, the quotation mark, and I have the number of the representation. I'm just going to put that, let's say, put the same thing, 20. You can choose anything you want, and I just put the notch equal to false in order to make the presentation of the box plot much susceptible. Let's see. I run the model, Control Enter, and you see that if I zoom the model, you see that still it somehow produces a similar somehow result with the quadratic model that we had. There are substantially less variation between the data. If we trace, for example, the mean of each box plot, they are not drastically going up or going down. They are essentially with tiny oscillations from, I should say, the mean of the true values, and the size of the box plot essentially shows the same thing. And essentially we conclude that the quadratic model and the cubic model, they produce a better realistic of, I should say, of original data sets when we replicate the data by those models. However, we assume that quadratic model is going to be a better model because parsimoniously we prefer the simpler model. Quadratic model is a simpler model compared to the cubic models. Then we just stick to the simpler model. That's the principle of the parsimony. Then the cubic model, it shows that it's the better model when we choose the model, I should say, in the Bayesian framework. Just by a simple intuition and idea that the model is good if it can produce its own data, that it just built that model itself. And essentially that's the thing which I wanted to talk about. And also, as a final thing I just wanted to mention, you can also go ahead to include the term of, let's say, for example, to the power of 4, to the power of 5th of the weight with respect to, let's say, the height, with respect to the weight, and essentially do not see that much differences. After the cubic terms, there is not, I should say, a substantial improvements in the predictive power of your model. Then essentially that's the trick. Normally we just try the second power, the quadratic model, and the third power, which is the cubic model, and we assume that we should not expect to see drastic improvements in the predictive power of a model after the third, I should say, power, of after the cubic model. Then that's the thing I just wanted to finish this part of the tutorial as a diagnostic one of how to choose a model. On the next tutorials, we just start with a completely new materials on the Bayesian regression analysis.